Yeah, good evening, and thanks for coming to this talk by Aditya Nema, who is currently an assistant professor at IIT Gandhinagar. He has just joined, apparently on temporary appointment. So Gandhinagar seems to have this ability to provide appointment before they are actually hired. So this is amazing. That you should also try this out, I think. So he received his master's and PhD from STCS, what is it? Systems and Theoretical, no.
Yes,
School of Technology and Computer Science. Thank you. School of Technology and Computer Science at TIFR. His PhD was under Pranab Sen. So it was in the area of quantum information theory. So following his PhD, he has had a couple of postdoc appointments, one at Nagoya University in Japan, and another more recent one, which is just completed at RWTH Aachen in Germany. And so he has literally just joined the IIT Gandhinagar W department like a month or so back. And we'll looking forward to hearing more from him over the years. And so with this, I will let him go ahead and give his talk on the decoupling theorem in quantum information theory. Thanks.
Okay. So first of all, I would like to thank Professor Kashyap for giving me an opportunity to visit here. It's always good to be here after a long interview. Okay. Okay. So I would like to thank Professor Kashyap for giving me an opportunity to visit, and every one of you for being here at this point of time. And before starting, I would like to apologize a bit, as my laptop conged off last night. So I had to remake all the slides by hand. So I hope that happened for good. It can be more interactive this way. And I don't intend to rush at all. So please feel free to stop me at any point of time if something is not clear. So I'll be talking about one of the mostly applicable and widely applicable theorems in quantum information theory, especially like the Shannon version of quantum information theory, which is the decoupling theorem. We'll see a couple of its applications and a way to de-randomize that particular decoupling theorem. And I'll explain what I mean by de-randomization as we go along. And I'll include all the basics in between. So please feel free to stop me if something is not clear, if there are any doubts. Okay, so before starting anything, a typical quantum system looks like this. So this is a typical quantum communication system. This is very analogous to our classical communication system. So there's an input vector, which is essentially a quantum state. I mean, just for simplicity, I've written it as a vector right now. It can be a matrix. And I'll describe shortly what I mean by a quantum state. It goes through a quantum encoder in order to guard against the noise that can be introduced by a quantum channel. Then the output of this channel goes through a decoder, and I can get either a quantum state as the output or a classical probability distribution as the output. So in processing information through a quantum system, there are two possible outcomes. One is either it can be a quantum state or it can be a classical probability distribution. Okay, and we'll see what does these means and what will be the outcome and how the system is essentially employed, or what are these individual components. This is answered by the so-called postulates of quantum mechanics. Other than that, we don't need anything from quantum physics other than the four basic postulates of quantum mechanics. So we'll start out with that. Before this, what is a quantum state? So it is nothing but a unit L2 length vector. By L2 length, I just mean that so the length is evaluated with respect to a usual Euclidean norm. So its L2 length will be 1. Then it belongs to a finite dimensional vector space. We'll always consider finite dimensional vector space over complex numbers, and that vector space will be complete. I mean, we don't need this feature for this particular talk. And a complete normed vector space is known as a Hilbert space. So the traditional terminology is that a quantum state is nothing but a vector or an operator on a Hilbert space. Now, after this, all these encoders, channel and decoder, they all can be thought of as nothing but quantum channels. These are linear transformations on the vector space of linear operators, essentially. So it will take an input as an operator, and the output will also be an operator. Similarly, what I get at the quantum decoder is it's either a state or a matrix. And if I want to get access to classical data, which is encoded or embedded in the quantum state, then I have to apply something called as measurement. Okay? Now, what these things are, we'll see. Yeah. This thing. So here, yeah, so it can either be a particular photon, which is in one of the particular polarization state that can be thought of as a quantum state. Okay, so now we come to the postulates of quantum mechanics. So like as I said earlier, quantum states are nothing but either vector or matrices in a Hilbert space once we fix a particular basis in order to represent the matrices. Then typically, so a quantum state is nothing but analog of a classical probability mass function. So since we are working, we are only considering finite dimensional quantum systems for now. That is why, like for the particular, or the rest of the talk will only be working with the finite dimensional quantum systems. So these quantum states, they are nothing but quantum analog of classical probability mass function. So we will not go to the density functions. And when I say that a quantum state is a matrix, it has the following property, that it is positive semi-definite and its trace is 1. So like one quick way to see that how does this can be viewed as a probability distribution, or how is this a quantum analog of a classical PMF. So if I have a classical PMF, let's say over an alphabet script X, then I can write it as a diagonal matrix with these PMFs lying on the diagonal elements of that matrix. So this will have the property that it is positive semi-definite and its trace is 1. So like this is one quick way like to keep in mind that a quantum analog of a classical state is nothing but such a matrix with these two properties. Then there are two notions of quantum state. One is either a pure state or a mixed state. So when I say that a particular quantum state is a pure state, all I mean is that the underlying density matrix is of rank 1 and it can be written as a column vector times a row vector. So we'll see what this notation is. This is just the Dirac's Ket notation. So when I write like this fancy Ket X, it means a column vector. And this is the dual of this column vector, which is known as like a bra of X. So essentially, this is just a rank 1 operator. And a state is known as mixed state if its rank is strictly bigger than 1. And I call like all the matrices with rank strictly bigger than 1 as density matrices. And the matrices with rank equal to 1 as pure state. So that is the terminology that will follow. I mean, it doesn't make like much of a difference what I call it. But the essential property that I want is it should be positive semi-definite and its trace should be 1. So this is the first postulate of quantum mechanics. Then what is like essential difference between a classical state and a quantum state? So a deterministic classical state will either be like a bit 0 or a bit 1 with probability 1. Like I cannot say that a bit takes a value 0 and 1 at the same time with some weights. Whereas in quantum, like the bit 0 and the bit 1, they can constitute a state by adhering to a superposition principle. So by this, essentially what I mean is that a quantum state can be written as a superposition of the bit Ket 0. So this is nothing but a quantum analog of the classical bit. So essentially, this is a vector of length 2, where 1 is like the first element and 0 is the second element. Similarly, this is a vector of length 2 with the first element being 0, second element being 1. Or like this can be viewed as I cap and j cap in like our usual C2 plane. And they have the property that the modulus of alpha square plus beta square is equal to 1. This is just to ensure that this is essentially like a quantum analog of a classical state. Okay. So yeah, and these notations, they are known as Dirac's Ket notation. Then, so a typical 2-level quantum system where essentially all I mean is that the underlying Hilbert space is of dimension 2, and I'll be representing any state using linear combination of the Ket 0 and Ket 1 is known as a qubit system. So if I have like, let's say just a state Ket 0, I'll say that it is a qubit 0. If I have a state Ket 1, I'll say it is a qubit 1. Okay. Now, furthermore, like there's a non-trivial and a quite surprising phenomena in quantum mechanics, which is known as entanglement. So we won't go into like the physics of it, but for us, like an entangled state just means if it cannot be written as tensor product of two states. So I'll like come shortly what is a tensor product, but for now, just assume it is some fancy notation. So like an entangled state is a state of this form where the first system is in state Ket 0 and the second system is also in state Ket 0. Similarly, it can be in state Ket 1 with uniform probabilities. So it can be where? Here? Yeah. So this is the definition of an entangled state. If it cannot be written as, correct. Sorry, that's a typo. Yes. So yeah, I'll say in the next slide what it means and what the symbol means. Yes. Yeah, but that's correct. Yeah, the summation should not be there. Yeah, it should not. It is nothing but a bit 0. I can give Alice the bit 0 and Bob the bit 0. Similarly, I can give like another bit which is 1 to Alice and Bob with equal probability. So like there is a difference between a classically correlated state and an entangled state. Okay? And in order to like just understand what is the composition of two quantum systems, like we need the formalism of the so-called tensor product. So like when I say tensor product, all I mean is this fancy like circle and a cross notation. So if I am working with, let's say, K systems, then the composite system is essentially governed by the tensor product of these Hilbert spaces. Now, there is a way to define tensor product in an abstract way and in a basis independent way, but we won't go there. So we don't need it right now. So all we need is fixing a basis of each and every of these individual Hilbert spaces. I can define a tensor product basis, and then I can represent the system or any state in it via the so-called Kronecker product. So like at an operational level, all I mean is that if I take, let's say, tensor product of two vectors, A1, A2, B1, B2. So this is just same as just taking A1 and multiplying it with the vector B and A2 multiplying it with the vector B. So if this is a two-dimensional system, this is a two-dimensional system, the tensor product of these will be a four-dimensional system. So that is all we need. And similarly, I can do this for matrices. So this is just known as the Kronecker product of the matrices, where I'll multiply each element of the matrix N with every individual element of the matrix M and fill this matrix. So yeah, and we can count the dimension, like I mean, it will be the dimension of this times the dimension of this. So essentially, this is the tensor product of two matrices. Okay. So if I were to go back, and now this makes sense that I can like write this in a four-dimensional Hilbert space. And if I try to write it as tensor product of two-dimensional vectors, I'll not be able to do this. Like this is like a very simple exercise to be checked. Okay, then the next postulate is like what that tells us what quantum channels can be. So it essentially says that a closed quantum system. So by closed, all I mean is that a system and its environment, we are treating them as a single system. So we won't be worried about what environment is doing on the underlying system. So that is known as a closed quantum system, and it evolves according to a time-dependent Schrödinger's equation. Okay, so like these are just diagrams. We don't need any of it right now. So by this, all I mean to say is that if I have an input state rho, if it undergoes evolution which is noiseless. So noiseless in the sense like it is modeled as a unitary operator, then its action is essentially U rho times U dagger. So this dagger just means the transpose of U and every entry conjugated. So this is the action of a channel. So if I were to say that I have a noiseless channel, all I mean is that I have a unitary channel, and the output of the unitary channel is essentially this operator, which is matrix U corresponding to the unitary of the unitary channel multiplied with the input times the transpose conjugate of the same unitary that comes from the channel. Now, a noisy quantum channel is essentially a generalization of this, which is known as a linear. So because the channel is linear, and it is the so-called completely positive and trace preserving map. So like each and every term here like is self-explanatory. So first, let's see what trace preserving means. So all it means is that if the trace of the input, let's say rho, is 1, then the trace of the output of the channel will also be 1. So by this, what I mean is, suppose I have a channel N with input rho, then the trace of the output of the channel is equal to the trace of the input of the channel. So if the output is sigma, the trace of sigma should be same as the trace of rho, which was input to the channel. And since we will be working with quantum states or density matrices, this trace will always turn out to be 1. So this is the first thing. And the second thing, like first of all, like let's see what do I mean when I say that a channel is positive. All it means, if the input to the channel is a positive semi-definite operator, then the output of the channel will also be a positive semi-definite operator. Okay, so this is essentially extension of the classical property of the channel, or the property of a classical channel, that it maps input probability distributions to output probability distributions. And the action of classical can simply be like represented by multiplication of the input probability vector via a column stochastic matrix, or like a probability transition matrix from X to Y. So that's all this means. Okay, but quantumly we cannot write this. I cannot say that this n of rho is some operator times rho. So this cannot happen. Okay. So now what completely positive means is that if I have a, let's say, identity on an n-dimensional system where this n is generally bigger than equal to the dimension of the channel n, and I act on it on any bipartite state. By bipartite state, all I mean is that it is a state shared on two systems. So this is a matrix which lives in the tensor product of the Hilbert spaces on A prime and A. And if this output state turns out to be bigger than equal to 0, or if this output state turns out to be positive semi-definite, when the state tau was positive semi-definite for every value of the dimension n, then I say that the underlying channel is a completely positive channel. Okay. Now, a simple example of a channel which is positive but not completely positive is essentially a transpose channel. So if all my channel does is transpose, so if it transpose all the entries of the input, then it can be proven like via this definition that this will no longer hold, and it is not a completely positive channel. Nevertheless, it will still be a positive channel. Okay. So for a quantum channel, these two properties are essential, that it should be completely positive and trace preserving. Okay. And the final postulate that, so we won't be needing this, but like I'm just saying this for completeness, that if I want to extract classical data, which is there in the quantum state, then I need to perform a so-called measurement, where a measurement mathematically is just represented by a set of positive semi-definite operators, lambda m, ranging from, let's say, 1 to d, with the property that each and every of this operator lambda sub n is positive semi-definite. And when I sum over all the m of these operators, this will essentially be identity. So this is what I'm saying, that if I sum over all m, these operators, they sum up to identity. And what is the outcome? So when an input quantum state is given to a measurement operator, the output is essentially a classical random variable m, which can take one of the d possible outcomes with the probability trace of rho times lambda m. Yeah, with this probability trace of lambda m times rho. And why this completeness relation is needed? Essentially, if I sum over all m, this should be a valid PMF. So for this summation can be pushed inside the trace. This will turn out to be identity, and I'll get this to be 1. So like this is well in conjunction, like with what we understand from probabilities. Okay, any doubts so far in the postulates? Like we'll be using all these things. Normalization. Where?
Something being positive but not completely positive. So what is the channel there in question?
Yeah. So the channel is a transpose map. So all the channel will do is it will swap rows and columns.
Rows and columns, I see.
Yeah. So with that, like I can easily take, okay, so the way to show that is I'll take an entangled state, which I like mentioned in
between two systems, right?
Exactly.
Okay.
Yes. And then it will turn out that this is no longer a positive map. It will have a negative eigenvalue.
Oh, I see. Okay.
Okay, so now this is like the last review point. After this, like we'll get done with all the quantum mechanics that was there, like even though we didn't get into it. So essentially, any quantum channel, a CPT map, has two representations. So as I said earlier, I cannot write the output of a quantum channel as an operator times another operator. That cannot happen. So the way a quantum channel can be represented is like there are 4 equivalent characterization. I'll just mention the 2 here because this is what we'll be needing for the rest of the talk. One is known as the Choi-Yamiolkowski representation, or there is a matrix corresponding to a channel n, which is essentially defined as follows. So I'll start out with a maximally entangled state on systems A and A prime. And then I'll send this through the joint channel identity on A prime, tensor product with the channel n from A to B. So this underlying operator is known as the Choi matrix of the underlying channel. Okay? So this is one way to represent a quantum channel. Now another way to represent a quantum, and if I were to recover like the input from the action of this Choi matrix, it is essentially governed by this. So if I want to recover like what was the input to the channel, so all I need to do is multiply the Choi matrix of the underlying channel with rho transpose tensor identity, and this will give me n of rho. I mean, this is a simple calculation. So a way to see this is all I need to do is I need to like express this in some basis, and one part of it will go with this identity, stays the same. So this can be written as summation of some, let's say, states of form. So okay, so this can be written as summation of tensor product of 2 operators, and this joint operation. So identity will act on the first operator as it is. Since this is a linear operation, the summation will come out, and it will be where the channel maps the other operator in the tensor product. So that's how this can be written. And it can be shown like this is like essentially the postulate that the output operator or the Choi matrix of a channel is essentially non-negative. So this is all it means. Yeah, it is positive. Yes, it's positive semi-definite. Correct. Yeah, it can have 0 eigenvalues as well. Yeah. Correct. Yeah. Yes. So generally, like what one does is, this has to hold for all A and A prime essentially, and B is the output of the channel. Yeah. And the way this state is defined, so it's an input state to this joint channel, and this is defined over systems A prime and A. That's all it means. Okay. So like if I were to write this, I can write this as follows. So when I say a maximally entangled state, so let's say it lives in a d-dimensional Hilbert space, then this is essentially written as get I over square root. Okay, so I guess this is what Naveen was mentioning earlier, that this normalization was specific. And like this get I is nothing, but it is 0 everywhere and 1 in the ith position. Okay. And when I don't write this get notation, when I write something like this, so the definition of this is, so this is summation over I. So this is 1 in the ith position, and this multiplied with this. This is the ith position. So this is an operator. So yeah. So this is on system A, this is on system A prime. So essentially like phi can be written as summation ij get I bra j on A tensor get I bra j on A prime. Now when I apply channel on it, which is identity tensor n, so this identity stays as it is, and there will be an application of n on this. So this is an operator, and essentially the thing is that the Choi matrix is bigger than, yeah, it's positive similarity. Okay, and another analogous representation, like they can be shown that they are exactly equivalent by simple linear algebra, that this is known as the Stein spring representation of the underlying channel, that corresponding to a channel n, there's always a unitary or an isometry on an extended system A to A tensor E. And the action of this is as follows. So it is essentially like a multiplication of unitary, since it is over like the extended system AE. The input is essentially rho A tensor any state that I want on system E. So there's not any fixed thing. This can be any state multiplied with U dagger, and then I'll trace out the E subsystem. In the next, like I'll quickly explain what trace out is. Trace out just means that if I have operators of form A tensor B, and if I say I'm taking a partial trace with respect to system A, all I mean is I'll take the trace of this, and this will remain as it is. Now, if a matrix cannot be written as a direct tensor product, I'll write it in the basis, which is the tensor product of the underlying two Hilbert spaces. And then I'll take trace of the first subsystem, and it will be like a linear superposition of those terms. Okay? So this is essentially like equivalent to like taking the marginal of joint random variable x and y. So this is the analog. So partial trace is the analog of the marginal of joint random variables of the PMF of joint random variables. Okay? So essentially like, yeah, he is the person who gave this representation. Yeah. Okay. So like, yeah, if I were to just explain very quickly what I mean by partial traces. So suppose I have trace out system A of x on A, y on B. Then this is essentially defined as trace of x times the system y on B. So this will just be an operator on system B now with the scaling of A. And if I have, let's say, an operator M on AB, then I can write it as sum over ij. Let's say M ij on A tensor M prime ij on B. And then when I take a partial trace with respect to A here, all I need to do is take a trace of this. This tensor product will no longer be there. It will just be a multiplication. So this is this operation, and this is also linear. Okay. And now we come to the quantum entropies. Okay, because this is what we'll be using in order to understand what a decoupling theorem is. Okay. So like before we go here, like so far I hope everything is clear. Yeah. Yeah, this is x on the system A. When I write this, I mean x on the Hilbert space A. So thus, yeah. This, yeah, this is trace of x times y on B. So it's just a scalar. Yes. So partial trace will just give me the output on the system B. And like, oh, okay, okay. Yeah, yeah, okay. Yeah, okay, okay. Sorry about this. And it can, like abstractly in a basis independent way be defined as like adjoint of tensor with identity. Okay, I don't want to go there, but like, so all it means is this. So let's say I have trace of system A on a matrix M, which is on AB. So this is a state on system B alone. If I take its Hilbert-Schmidt inner product, so everywhere I'll be dealing with Hilbert-Schmidt inner product. With that, all I mean is that the inner product of two operators is essentially defined as trace of X dagger Y. This is the definition. And if I have this with some operator N, which is on B, then the definition of this is essentially this. This is M on AB, identity on A, tensor N on. So this is how partial trace is defined abstractly. But we don't need any of this as of now. Okay, but like the key takeaway is that this partial trace is nothing but a way to take marginal over quantum states. Okay, yeah. So before this, like what are quantum entropies? So like the favorite one would be, let's say, the quantum analog of the Shannon entropy. So this is also known as the von Neumann entropy. So I'll write entropy of the system A evaluated over the state rho A. So by this, all I mean is that the system is in the state rho, and I want to define the entropy of rho. And this is essentially defined as minus trace of rho log rho. Now, the reason like which comes into play here is that the state rho was essentially positive semi-definite, and it is also Hermitian. Okay, so this I didn't say earlier, but we'll also assume all the positive semi-definite matrices that we'll consider will also be Hermitian. So they admit like this particular decomposition, which is the spectral decomposition, that I can write it as eigenvalue times like the projector onto the eigenspace, or essentially Ket Bri, and it has all these properties. And then I can define what is rho A log rho A. And log of this operator is nothing but log of lambda I, keeping these projectors intact. And in order to like define this, I need to ensure that all these eigenvalues are essentially like bigger than 0. And if I have 0 times log 0, as we do in classical information theory, that entropy is 0, we'll assume this is 0. Okay. So next is the notion of the conditional entropy H of A given B. So this is in a different color because like there has been a lot of work in understanding what does it mean to condition a quantum system. So we won't go here. Like the way it is written, it seems very trivial, but essentially like this came about after some thought. So H of A given B can be defined as H of AB minus H of B. So this, when I write H of B, it just means that I'll trace out A system from the state rho AB to get rho B. This is all I need. Okay. Yeah. So yes, and now so we'll be working with the one-shot conditional entropies, and all of these will be the quantum entropies. And this is the following definition. So now we are moving on to something a little more advanced and more quantum. So essentially, if I were to define like the conditional Renyi 2 entropy of system A given B evaluated over the state rho AB, then this is essentially negative log of a minimization over all the marginal states on the system B, sigma B, trace of identity tensor sigma B to the power minus half times rho AB square. Okay. So for this, like a quick way to see this is like, this is nothing but if I take B to be a trivial system, then this is nothing but the collision entropy, that probability the two random variables are equal essentially. Like I'm not doing that exercise here, it will take a lot of time, but I mean, this is the generalization in the quantum regime of the collision entropy. Okay. And for now, like for us, the important part will be what is, so this trace square of some operator can be viewed as L2 norm square of some operator. So all I want you to take away from now is that this conditional Renyi 2 entropy is nothing but L2 norm squared of some operator. Okay, and we'll see what that operator is as we move next. Okay. And the another entropy that we'll be working with is essentially the conditional min entropy of A condition on the system B evaluated over the state rho AB. And this is essentially defined as negative log of maximum eigenvalue of rho. So this is an equivalent characterization that this is minimization over all the marginals on the system sigma B, such that sigma B is bigger than or equal to 0 and rho AB is less than or equal to identity A times sigma on B. And when I like compare two matrices, I mean that difference of this matrix and this matrix is positive semi-definite. So this is the notion of comparison. Okay. So, but for this, like the intuition to take away is that if B is trivial, then the min entropy is nothing but negative log of maximum eigenvalue of that operator A. So like this is the takeaway from here. And like it can be trivially shown like just by comparing these expressions that H min of A given B is less than or equal to H2 of A given. I mean, this also justifies why this is min, this is not min. Okay, now what do we want to do with one-shot entropy? So like traditionally the way one-shot information theory, even in the classical setting, it goes is first one tries to prove a one-shot result, then takes the asymptotic ID limit and show that it converges to the underlying Shannon entropies. So what I mean by this is I'll tell you now. So suppose I want to see some asymptotic equipartition property for this quantity AB on rho. So for this, all I need to do is I need to raise this rho to the tensor power n, and all the underlying systems will be on n-dimensional Hilbert spaces now. And an AEP-like property would mean that if I divide the entropy of the nth extended system by n, take the limit as n goes to infinity, I would want that this should essentially be equal to the conditional von Neumann or the conditional Shannon entropy. But with these entropic quantities, the way they were defined as such, like this does not happen. So that is why what one does is one replaces these entropies with their smoothed version. So what smoothed version means is that I'll evaluate this formula, which like we have seen earlier, it is nothing but L2 norm of some operator square. But now that operator will not be the original operator, but a perturbed version of it, which lies in an epsilon ball around rho. Now this epsilon ball is like, it can be defined with respect to any norm. In quantum information theory, one generally defines it with respect to the Schatten L1 norm. And Schatten L1 norm, all it means is, so I'll just say here. So if I were to define, let's say L1 norm of the operator A, this is essentially trace of square root of A dagger A. This is the definition. And if I were to define the L2 norm, the Schatten 2 norm of it, this is essentially trace of A dagger A square root. Okay. So these are the two definitions that we won't need any other norm. And like why this nicely adheres to AEP is that a slight perturbation of rho to rho prime does not make this quantity to diverge. I mean, this needs like a bit more explanation, but for now, like just to like keep in mind, why are we going for the smoothing essentially? So the reason is just that I want to have an AEP-like property, which the smoothing gives me. So what smoothing gives me is that if I take first limit n goes to infinity, then limit epsilon goes to 0. And if I evaluate h2 epsilon over the nth extended system, where the extension is, this is important here, the extension has to be taken like over identical copies. So essentially it has to be IID state, rho tensor n. Then this goes to h of A given B of rho. Okay. So like these are the properties that we would want for this entropies. Okay. So is this thing clear so far? Like the only thing that I have hidden so far is that why is it that if I perturb rho to rho prime, this particular quantity evaluated with respect to rho prime does not diverge. Okay. But this is a technical thing that we can like assume for now. Yeah. So if I were to define the square root of an operator, yes. Yeah. Thanks for. Yeah, of positive. Yes. So that's what I was about to say. That first the operator, the underlying operator should be positive semi-definite. So I can write A as summation I, lambda I, theta bra I. All these lambda i's, they have to be bigger than equal to 0. And square root of A is essentially square root of lambda I, theta bra I. And essentially like any function that will be defining on the operator A will just be summation I, f of lambda I, theta bra. So this is the definition. Yeah. Two different systems. Yes. So the way to see this is that there is a state rho AB. This lies in the Hilbert space HA tensor HB. And the way one thinks about it is, let's say Alice has the A part of the state and Bob has the B part of the state. Or like even at a single lab, one can prepare a joint bipartite state, essentially. So I'm making like I'm interacting, let's say two photons essentially and looking at their joint state. Okay. So like when I write H of A given B or any entropic quantity, all I mean is that this is H of the joint state rho AB, which is essentially minus trace of rho AB log of rho AB minus H of B. So that's all this means. Yeah. So if this B is identity, then like this is just the quantum analog of Shannon's lossless compression theory. So this H of A it tells me, yeah, that is AEP. Yeah, I mean, that is not in the one-shot regime, yes. Yeah, yeah. So like if I were to come up with a coding and decoding scheme, I have to go to like an equivalent notion of the random coding argument by taking codes of letter n. And then define like analogs of typical subspaces and doing like the similar thing. And then at the end showing that as n goes to infinity, the optimal rate is essentially entropy of A. Okay. Yeah. So that is like a in the quantum world, it's known as Schumacher's compressions. Okay. So now we come to the main theorem. Like so far, any doubts on the fundamentals? Okay, like because this like I'll just try to convey the high level intuition, and the other things like that can be assumed. I mean, they are not so important. Okay. So essentially what the theorem is, so the task is as follows. So there is a state on system A, which is essentially an entanglement with some reference system R, and no one has access to this R. So the bipartite state is rho AR. Okay, so this need not be pure, this can be mixed. And the task is I want to apply some channel or some processing map only on the A subsystem such that the output is essentially a tensor product system. So the channel that I'll apply is, let's say, a channel from A to B. Maybe B is isomorphic to A, we don't know. So I can take any channel that I like, and I want to understand, can it happen or find the conditions under which the output of this particular diagram is essentially a tensor product system. So for this, like the theorem which was first given in the so-called mother of all protocols, I mean, that was the title, the fancy title given to a particular paper. But essentially, it's known as the decoupling theorem in the modern language. And the way to do this is as follows. So I have to apply a random unitary on the system A. Okay, so this means that I'm not doing anything on R and applying unitary only on the system A. So this is just essentially taking I tensor U, applying on the state rho AR. And an important fact is that this U is chosen uniformly at random from the unitary group. So essentially, this is done via the so-called Haar measure. Okay? And then I apply any channel or any CPTP map that maps A to B. And the resultant state, which is on system B and R, because here after this A, this channel has mapped the system A to B. So I get a state on system BR. And I want to see that when can it happen that this state B is close to the state of form something on B, tensor something on R. Okay? So this omega B is nothing but the reduced state of the Choi matrix of the channel A. This is what we started out with, that corresponding to any channel, I can define a Choi matrix that will be on the systems A prime B. If I trace out A prime, what I get is this fancy notation. This I call as, so this was the Choi matrix. And if I trace out A prime, this is the output state that I get. Okay? So this says that if I take expectation over all the Haar random entries, essentially this is an integration with respect to the Haar measure. And this is essentially upper bounded by 2 to the minus half conditional to entropy of A given B evaluated with respect to omega, because omega is essentially this state on system A and B. And H2 of A given R evaluated on the input A, on the input rho. Okay? So this term here is reminiscent of the input state rho AR, and this term here is reminiscent of the channel that is acting from A to B. But in order to make this work, I do need an intermediary step, which is essentially choosing a unitary uniformly at random. Okay? So like very morally speaking, this is nothing but a quantum analog of Shannon's random coding argument in the quantum version. Okay? So, but this is just morally, I mean, it is not a direct extension. Okay. So the next thing is like, okay, so why did I go to AEP? What I want to do is essentially I want to prove a coding theorem. So given a channel, I want to find the capacity of a quantum channel. Okay, and I want to find it in terms of some entropic quantity that I already know. I don't want to use single shot entropies, because like I know from Shannon's channel coding theorem that the capacity of that channel is essentially like the maximum of the mutual information. So I want to prove some such theorem here. So at the end, I would want to take all these to the tensor power n and evaluate the limit as n goes to infinity. So I know that like these quantities, they don't adhere to the AEP. So I need to replace them by their smoothed versions. Okay, so that can be done like with a lot of effort. It's not at all trivial to do it. And the main point in like coming up from a non-smooth to a smooth version of the decoupling theorem is essentially perturbing the channel tau to tau tilde, such that under some notion of distance between the channels, now it is no longer the notion between two operators, okay, that tau tilde is also close to tau. and then evaluating this decoupling theorem for that perturbed tau and tracing it back to the original operator tau. So I mean, this is a tedious process. So this was a separate paper, in fact, and it showed that one can indeed come up with a smoothed one-shot version of the decoupling theorem. And I'm saying this is a one-shot version because here, like all the states and the channels are applied just one. Okay, and with this, then it was shown that since AEP holds for all these quantities, the overall rate can be h of A given B plus h of A given R for sufficiently large n with some deviation epsilon. Okay, so now let's take one example or an application of this. So we have seen that in order to achieve decoupling, I need to apply any channel on the state U known as conjugation. So whenever you see a fancy dot, all it means is U rho, U dash. So if my channel that I'm applying for decoupling is essentially a partial trace channel, a marginalizing channel, then this gives rise to the so-called fully quantum Sleepin-Wolf theorem. So it is essentially distributed message compression in the quantum pool. Okay, so this is the task that suppose Alice and Bob, they have a state AB, which is rho AB, and which is purified with some reference R. So the joint state on reference A and B is a pure state denoted by psi on RAB. This is what it means. Now Alice would want to apply some encoder, Bob would want to apply some encoder, send some classical bits. So the intention to apply encoder is to compress these states on A on that they have access to A and B. And the role of the receiver, Charlie, is to apply a decoder receiving receiving quantum bits from Alice and Bob, is to output two subsystems A and B hat such that the resultant overall output state is close to the resultant input state. These are the rates. Yes, these are the number of qubits. Yes. So here the communication is all quantum. Yeah, and for a quantum system. Okay. So like one strategy for this, I mean, again, so like I'll give a high level intuition, but this needs some proof, and the proof revolves around the typicality arguments and the decoupling argument. But it is essentially that Alice, let's say, wants to do a Schumacher compression. So Alice can compress at a rate of h of A. So RA is h of A. Okay. And then what Bob will do is Bob will apply the decoupling theorem by choosing this operator as partial trace. So he'll view B as composed of two subsystems B1 tensor B2. So essentially you can think of as the system that is transmitted is nothing but the typical the dimension of the typical subspace, and the state which is traced out is essentially the atypical path. Yeah. So then Bob will apply the fully quantum Sleepin-Wolf theorem or the decoupling theorem, and it can be shown that the number of bits that Bob needs to transmit is essentially minus h of B given R. So this is again like a surprising phenomena in quantum information, that the conditional entropy can be negative. Okay? So like essentially, like if I were to map this to classical thing, it might seem that, oh, okay, this is always a positive quantity. What does it mean for Bob to transmit anything negative? No. So this quantity will be negative. Okay, that is why like a minus of it will make it positive. But this is essentially just the application, the black box application of the decoupling theorem. And the sum rate in that case will be then h of AB, which is what the Sleepin-Wolf region is. So essentially, RA is h of A given B, RB is h of B given A, and the sum rate is h of AB. So that's why if the underlying operator used for achieving decoupling is just a partial trace, it was given the name fully quantum Sleepin-Wolf theorem. Now the next thing is like, what if I were given a channel N and I want to find the capacity of this channel? So this is another application of the decoupling theorem. So all one needs to do is, so there are several notions of how to define the capacity of a quantum channel. One such notion is entanglement transmission. So all this means is that I want to transmit 1/2, let's say A prime of an entangled state through this channel A, and I want to see what is the maximum dimension of the underlying subspace of A prime that can be transmitted reliably. So this is like the definition of entanglement transmission through a channel. So this is also known as entanglement transmission capacity. Another equivalent notion is if the channel generates entanglement across the output. Okay. Now all this might be abstract, but so for now, like we will just focus on entanglement transmission, and the task is as follows. So I start out with a joint state on A prime and R, and my goal is that at the end, Bob should end up with a state phi prime, such that the state phi prime on B and R is very close to the state A prime and R. Okay, or whatever best I can extract. So for this, what I'll do is I'll project the state on system A prime via a Haar random projector onto a smaller subspace A, which is embedded in the space A prime. So this is my encoding. Then I'll apply this unitary channel. And here, so I'll use the Steinspring representation of the channel N. So this is the application of a random unitary from the decoupling theorem. And this is essentially the Steinspring version of the channel that is applied. So generally what I want to do, I want to say this is my encoder, this is my channel. This can just be thought of as like this. Then the output state here is on the systems R, E, and B. So my super operator or my channel, which is used for applying the decoupling, like if I encompass this as some encoder to achieve decoupling, that will essentially be tracing out the B subsystem and looking at the reduced state on R and E. Now, if it can be shown that R and E are independent, that is, if the starting reference, it does not meddles with the channel environment, then indeed there is a way that I can recover the entire subspace A here that was encoded via random projection. And this is essentially like the coding and decoding scheme. And in this process, like the decoupling is between the channel reference and the channel environment. And there's a theorem known as Ullmann's theorem, which gives the decoder for free. Okay. So like for this, like just the takeaway is that if I can achieve decoupling between the reference and the channel environment, I don't have to worry about what the decoder will be. Ullmann's theorem guarantees that there exists one decoder, and we are happy with that. And in such a way that the output state will be this maximally entangled state on the system B tilde I, which we don't care. We care about the state on state A hat and R, and this will be very close to the state that I have here, which in turn will be close to the state psi of A prime R. So now all I need to do is like evaluate what is like the decoupling theorem giving me. So essentially the first term, which was, so the first term, which was coming from rho A prime R. So we start out with this as a maximally entangled state again. And projection onto Haar random space gives me that H of A given R is essentially log of mod A. I mean, this is just a trivial calculation by writing the state and evaluating the entropy. And then this is the part of the decoupling theorem. So it gives me that it is 2 to the minus half H of A given R. So this will be square root of like the inverse of mod A of dimension of A. So this is the subsystem. So this is the number of qubits that will be transmitted in order to regenerate A correctly at the decoder or transmit A reliably at the decoder. And this is the other term, which is like reminiscent of the channel, which is minus H of A given B. And this is the expected error probability. And if I like upper bounded by delta, all I'll get is that the number of qubits that needs to be transmitted are essentially upper bounded by minus H of A given B plus delta. And this quantity is known as the coherent information, which is the quantum analog of the mutual information. So essentially the quantum capacity of a quantum channel is nothing but this funny looking quantity, coherent information, which is the negative of conditional entropy. Okay. So like decoupling theorem gives this. Now in the remaining thing, I'll just say like what have we done quickly. So what we want to do is, so this is a theorem in expectation. Like this is how we started out with the decoupling theorem, that the expectation of this quantity is governed by the entropies. Okay. Now we want to find what is the probability that this function is concentrated about this particular quantity, which is the RHS of the decoupling. So what I'll say is that this is roughly the mean of this random variable, matrix valued, this is a scalar of this random variable. And I want to find what is the probability that this function minus its mean bigger than epsilon, how it decays. I want to find this tail probability. Okay. Yeah, so I want to prove something like this. So this function is essentially the difference of the two operators in the L1 norm minus its expected value. And I want to get like an exponential concentration. And I don't want to use Haar random unitaries because like they are inefficient to implement. A d by d Haar random unitary, it would need exponentially many number of gates to be implemented. Okay. So like we want to replace this U by something which is more efficient, which we'll see shortly. Okay. And so in order to come up with an efficient implementation of a subset of unitaries that can be used in the same purpose where the decoupling or the Haar random unitaries are used, is essentially a subset of unitaries which is known as an epsilon approximate unitary T design. Okay. So we'll see formally what this means. But first, like the thing is, this design methodology, it works when the underlying functions are polynomial in the entries of this unitary. And so this L1 norm as defined is not a polynomial in the entries of U. So a trick is to upper bound it by L2 norm. So like, so here there will be a square, this is a typo. So this L2 norm square now of some different function, which we'll get by the so-called weighted coefficients, which I'll show quickly now, is essentially what we'll use to find the concentration from. And coming from the concentration of F tilde, we want to find the concentration of F and with respect to 1 norm. So this is the goal for the next thing. Okay, so I'll say all this. Yeah. So first, like, I mean, don't look at the entire set. Maybe it looks horrendous, but all I want is, so if I have an L1 norm of some operator n, I can upper bounded it as L2 norm of some like a modified version of this operator, where the modification corresponds to multiplying with positive definite matrices. So these are not, so these matrices don't have any eigenvalue 0, and it is conjugated by to the power -1/4. So this is what I call as a weighted Cauchy-Schwarz inequality. And the main task is to control these weights so that we can get an exponential decay in the decoupling tail. So this is the goal. Okay? And the second thing is that in the mean process, like ultimately what we have hidden so far is how to find this expectation with respect to Haar random unitaries. So what I want to find is expectation of U tensor to some operator M on U dagger tensor 2. So this is like a famous result in representation theory known as Schur-Weyl duality, which says that this particular operator, which is essentially expectation with respect to Haar measure, is a linear combination of identity and the swap operator, if these unitaries are taken to the tensor power 2. Okay? So yeah, so I mean, I had like a primer on this, but we won't go here. We'll just accept this result that if I have U tensor 2, where U comes from Haar measure, if I apply it on an operator M, take the expectation with respect to Haar measure, what I get is an operator of form alpha identity plus beta on F. A quick intuition is that there should be a linear combination of all the permutation operators, which is what is reflected from the symmetry or the rotational invariance of this Haar measure. So this is what I want to do. Okay. So like I'll skip all this essentially. Okay, and now what I'll do is first I'll evaluate what is the L2 norm squared of this function via weighted Cauchy-Schwarz, and the evaluation of expectation of this quantity will bring in the entropies, and this is where I'll use the Schur-Weyl duality. Okay. So this is that particular step that I want to evaluate finally this particular expectation. Okay, and it can be shown that expectation of just this quantity is essentially this particular quantity. I mean, this is not important. What is important is that this overall expectation is evaluated as 2 to the minus conditional entropies. So this is the takeaway from all this. Okay, so essentially this is what I mean, that finally when I evaluate expectation of L norm, I can write it as upper bounded by minus half of H2 of A given B and H2 of A given R. Now all this was when the underlying unitary was Haar random. Now when I go to T designs, so for yeah, so before T design, okay, just one quick note on how does one try to go from expectation version to a high probability version. Okay, so for this, a naive application of Markov inequality will just give me the expectation over delta, and this need not be an exponentially decaying tail, and it is not even telling me how sharply is this function concentrated about its mean mu, which is what we want on the whole. So we want that an overwhelming fraction of unitaries from the Haar measure, when they are used for this function computation, this function is concentrated around its mean. So this is what we want. Okay. But so the way to do it is the so-called Levy's lemma from functional analysis, which says that if my underlying function is Lipschitz continuous with the Lipschitz constant f, then we have such a concentration result, which is like a Chernoff bound. So essentially it decays as e to the power minus dimension of the system A. A is the dimension of the unitary which is applied, and here the randomness is over the unitary U. Then the deviation delta upon the square of the Lipschitz constant. So in order to prove such a concentration, the challenging task is to find a tight Lipschitz constant for the underlying function F. And for Haar measure, like it was shown that it's like the tight evaluation of the Lipschitz constant of F is essentially 2 to the square root of operator norm of the underlying state rho. Okay? And this indeed gives us this exponential concentration, and this is governed again by the min entropy. So min entropy is nothing but negative log of square root of this particular operator. Okay? So this operator just means this is an operator norm. All it means is the maximum eigenvalue of the operator rho. Okay? Okay. So now finally what we want to do is, our goal is to prove, so this is what we have done. So we want to prove such an exponential concentration where this U comes from something more efficient. Okay? And this more efficient is nothing but known as approximate unitary T design. And if the value of this design parameter T is log dimension of the unitary, which is log dimension of, which is log A, then there are efficient implementation for these T designs. formally all a T design means is that if I have a function P, which is polynomial in the entries of U, I evaluate its expectation with respect to this design, where I'll choose every unitary from this design uniformly at random. And I compare its distance with the Haar average if this is very small. So if this if this is upper bounded by delta over dt, then I'll say that such a unitary is nothing but a delta approximate unitary T design. Okay, so is the definition clear? So this is the meaning of the definition. So what I want to do is I know how to evaluate this quantity. I have to evaluate this quantity in order to find the expectation with respect to T design. And then I want to prove that probability f of u, where u again comes from a design, minus this expectation, it decays exponentially. So this is my, okay. Yeah. So for this, the first thing is this pu, we want it to be a polynomial, but we are working all the way with L1 now. So this is not a polynomial. So we need to replace this via weighted Cauchy-Schwarz to L2 norm square. So this is the first step. Okay. And then the second step is we also want to find the expectation with respect to design in terms of the smooth entropies. Now, since we don't have the symmetry coming from Haar measure, and to prove something is a smooth entropic quantity, we need to define like a variant of the conditional to entropy. So this was another result in this work, that there is no way that one can just prove the good old, one can use the good old smoothed version of conditional to entropy and prove and compute the expectation in terms of the smoothed entropy. So we need to define a new variant of this, and this is essentially defined by shaving off the smaller eigenvalues of the weights in the Cauchy-Schwarz. So this is the main technical thing. So what I intend to say here is, I mean something very simple, but it gets very complicated. So where, okay, so let it be. Yeah, so what I mean to say is that if I have a weighted Cauchy-Schwarz like this, which is sigma power minus 1 by 4 m sigma power minus 1 by 4 L2 norm, I have to control these weights in order to come up with a tight enough Lipschitz constant first, and second, I have to control these weights so that when I perturb tau to tau tilde, I still get an analogous entropic quantity. So controlling these two things gives rise to this new entropic quantity. Okay? And we want it to be smooth so that when we take AEP, which is also another new result, we had to prove an AEP for this quantity, which was not there earlier. So we were able to show an AEP for this quantity, that in the limit as epsilon delta goes to 0 and n goes to infinity, this quantity approaches the Shannon entropy. Okay. And finally, this is the takeaway, that we do manage to prove that probability that the tail of the function, of the decoupling function, when the underlying unitary is chosen from an approximate T design, it indeed decays exponentially. Okay. But the non-trivial part is the Lipschitz constant here is not the Lipschitz constant of the function f, which we have when the underlying u was chosen Haar randomly. And the reason for that is, if I work with that Lipschitz constant, I will not be able to compute the moments and prove this inequality because there is no Levy lemma known for designs. Okay, so we have to prove a new Levy type lemma for designs. This is first code. So this is what we do. And the Lipschitz constant is essentially of a modified function f, where the modification is first with respect to the weighted Cauchy-Schwarz to some f tilde, and then perturbing the super operator t in order to get a smooth variant again to get a function g. So the Lipschitz constant, which looks quite horrendous. So the first term is still the same, but this is another new entropic quantity. This is there just to ensure that I can prove a Levy type lemma for unitaries coming from designs. Okay? And we were able to show that if I work with a partial trace as my channel, then indeed this unitary can be chosen from log mod A design. So it will indeed be efficient. Okay? And finally, we even proved the AEP for these new entropic quantities. And the use of these new entropic quantities was found in another paper where we were trying to find one-shot fully quantum capacity of a quantum multiple access channel. Okay, so that is where these entropies show in very explicitly. Okay, so we won't go into this. Yeah, so just the final, I'll just take 2 more minutes. And I'll just show how these entropies look like. So essentially, what is that shaving of the smoothing that I'm referring to? So this H2 epsilon delta, the new entropic quantity, is essentially negative log of minimum of some perturbed version omega times like some state eta, okay, where this omega epsilon delta is the perturbed version of the marginal on B, and the perturbation is done in such a way that I'll shave off all the smallest eigenvalues of omega B, which sum up to at most 2 to the minus h max of epsilon. Like this is something that is to be taken care of. So this is one thing. And moreover, this eta is an operator which indeed lies in an epsilon ball of omega, which was the requirement of smoothing that we started out with. Plus, it should also satisfy the property that any vector which is in the support of this eta, it should project well onto the support of this marginal omega epsilon delta. Okay, so with this we can prove an AEP-like property. So that is where these two underlying states are different from the original state omega. And we were able to find application like essentially in physics in the phenomena of relative thermalization. And like a fancier example was, does black hole that evolves according to a design behaves like an information mirror? Okay, so we won't go into here. Yeah, so that's it. And like there were several works following our work. One was essentially like a privacy amplification and decoupling without smoothing. So here the goal was to like replace the entropies in the expected version of decoupling by Renyi entropies of order bigger than 2, as opposed to the entropy of order 2, which was the initial theorem by like Frederick Dupuis. Then we were able to use this in essentially finding simultaneous decoding schemes for achieving quantum capacity of a quantum multiple access channel. And then very recently there was a work where instead of Haar random unitaries, 2 wise independent unitaries, or essentially 2 designs were used, which bypass like a major bottleneck in quantum information theory known as simultaneous smoothing to use to approximate, it is applied in the multi-user information theoretics. Yeah, so that's all. And essentially like this work, it builds a lot on our work in this particular work, and it uses like the ideas from entropies which look very horrendous. So yeah, this.
Are there any questions for Aditya? So, I mean, instead of using all this, I don't know, connections
Designs?
with weighted Cauchy-Schwarz and Renyi entropies.
Yes.
I mean, are there versions of hypercontractive inequalities that could be used for similar effect?
Yes, they are there, but not for the decoupling theorem. So they are there when one analyzes the fidelity between the input and the output state, and there these notions of hypercontractivity are used. But the easiest way to prove an achievable result, this hypercontractivity will show up a lot when one tries to prove a strong converse for point-to-point quantum channel capacity. For achievability, the easiest proof is the decoupling theorem. And they're these 2 entropies, they're very natural. They are nothing but L2 norm of some operators, which can be upper bounded easily by this Renyi 2 entropy.
Okay. If there are no further questions, then we can just thank the speaker once again. And
thank you.